Hi, everyone. Welcome back. Hey, let's talk a little bit more about chemistry. And today, I would like to talk to you about the periodic table of elements. We're also going to discuss density. And then we'll also look at a special type of calculation involving temperature changes and heat energy. All right, let's take a look at the periodic table. If you heard about that before, well, I got one shown on the left-hand side of the screen here. That's the format that you will get for exams. I have a copy of this posted on Canvas. You should probably take a look at it sometime soon with the homework, for example, and start getting used to that. Okay, if you've never seen the periodic table, no problem. Let's start with the basics. So at the very, very beginning of learning how to do this thing called chemistry, we make a fundamental assumption. We say that, hey, everything in the world around us, you, me, the desk, the air, water, everything is made up of atoms. What's an atom? Well, it's the tiniest piece of material. So for example, if you had a gold nugget and you took a little piece of that and cut that little piece into a smaller piece and took that tiny piece and cut it again and again and again and again, eventually you'll come to the smallest chunk of gold. And what we imagine that to be, it would be a single atom of gold. And if you could cut it again, split the atom, the two pieces would no longer be gold. Okay, so the smallest piece of material is an atom. We call it an atom. And it turns out the atoms come in different flavors, different types. And every type of atom is actually listed on the periodic table. That's kind of cool. So let me get the pencil here so I can doodle on the page. So technically, all the different types of atoms are called elements. And all the different types are actually listed here on the periodic table of elements. And so we have gold. Maybe we can zoom in so you can see this a little bit better. So gold is hiding right over here. It's element number 79. It's got the chemical symbol AU. That's pretty cool. Silver sits right above it, element 47. And hey, there's copper. That's kind of interesting. They're all in the same column. That's not a coincidence. We'll talk about that more later. Let's see, what are some other elements, types of atoms you're familiar with? Helium. So your helium balloons filled up with these types of atoms. Neon signs are filled up with neon gas. So gases are individual atoms moving really fast, not stuck together. And so neon sign is filled up with one type of atom, the neon atom. There's oxygen. That likes to pair up. And then that's the form of oxygen we breathe in the air, O2. Okay, so switch different type of atom and you get a different material. Cool. Okay, some things you need to know about the periodic table. Well, there's plenty of things to know. First of all, you should know you don't have to memorize it. I know some classes they do, I do not. I think of the periodic table as a tool. You'll have a copy of that for your exam if you need it. Okay, but you need to be able to use it. You need to know a few things about the periodic table so that you know how to use it. So I got 5 things here that you need to know. First of all, elements can exist by themselves to form materials. Talked about gold already and helium. Iron, yeah. So if you have a whole bunch of iron atoms stuck together, you would know that as a block of iron or maybe an iron nail. Okay, so if you just have one type of atom all stuck together, a bunch of those atoms stuck together, that makes one type of material. But you can also mix and match, right? So it turns out if you take 6 carbon atoms, 12 hydrogen atoms, and that's a 6 over there off the screen, 6 oxygen atoms, you make up blood sugar. Okay, that's kind of cool and kind of important. It's also called glucose, the product of photosynthesis. It's kind of cool too. So plants know how to grab 6 carbon atoms, 12 hydrogens, 6 oxygens, and link them together in a specific manner to make something that is essential for life, blood sugar or glucose, which is actually kind of weird. You know what sugar is, sweet, white crystals, tastes great, but it comes from charcoal or diamond. That's the pure forms of carbon. Hydrogen gas is explosive, has no odor. Oxygen, you know what that is. You inhale that all the time. Wait, so oxygen from the air, hydrogen gas, explosive, charcoal, diamond, but mix those up, it makes blood sugar? Okay, that's just totally cool and weird at the same time. Okay, so mixing, matching makes new materials. What else do you need to know about the periodic table? Hey, most of them are metals. We already pointed out gold, silver, and copper. There's nickel over here and iron. You may not think of sodium as a metal, but in its pure form it is. Later in the course, I'll show you some pictures of pure sodium, and you'll look at it and say, well, that is a solid, it's shiny, just like a block of aluminum maybe. Oh, aluminum's on here too. Again, another metal. But not everything is a metal. We talked about helium, neon signs, those are not metallic. Those are gases. Oxygen gas, that's not a metal. Charcoal or diamond, not metallic. Yeah, so the pattern is, chemistry is full of patterns. One pattern here is that elements on the upper right of the periodic table tend not to be metals. The rest are metals, which is kind of cool because what I did for your periodic exam, sorry, your periodic table for exams, I darkened this diagonal line here that cleanly separates the metals left side from the non-metals right side. Very cool. So at a glance, if I ask you, hey, is sulfur a metal? You'd say, no, it's on the right side of this diagonal staircase. It's a non-metal. How about osmium? Osmium's on the left side of the diagonal. Must be a metal. Probably pointed this out in one of my other videos. Chemistry is full of exceptions though, right? So we're expecting one here, and we got one. Yeah, for most of the elements, if you're on the right of the diagonal, you're a non-metal. If you forget, check helium. Oh yeah, helium's not a metal, it's on the right side. If you're on the left, metal. I got gold here, I got copper here. Yeah, those are metals. Left side metal. Hydrogen. That's our exception. What's kind of cool about this periodic table is it's detached, it's floating like a gas. Yeah, so that's a visual clue that the letter H, element number 1, is detached, floating away from the periodic table. It should be over here with all the other nonmetals because hydrogen is not a metal. You know what? In fact, some earlier periodic tables places hydrogen right here, right next to helium and above fluorine, because it is a nonmetal, and it felt like it should be over here on the right side with the other nonmetals. Oh, but there's a better reason why we're sticking hydrogen on the left side. We'll get into that later in the course. Finally, the fifth thing you need to know is not everything is cut and dry. Well, you already saw an exception, so yeah, there you go. Yet another example of things not being black and white. Right side, non-metals, left side, metals. If you're touching that diagonal line, you're borderline. Maybe not aluminum, that's clearly a metal, but silicon, well, I twist your arm, is this a metal or non-metal? It's on the right side. You would have to say silicon should be a non-metal. But you've heard of Silicon Valley, where they make computer chips. Computer chips are made of silicon, and computers run on electricity. What conducts electricity? Metals do. So the metals are good conductors of electricity. Neon, oh, let's not use neon, but helium, carbon, charcoal, that doesn't conduct electricity, but silicon kind of does. Not really well, kind of conducts. We call it a semiconductor. So all the elements that touch the diagonal, so if they're touching the staircase, you can call them metalloids or semiconductors, because that's what they are. But again, there'll be times when I say, you know what, it's either a metal or non-metal, tell me what it is. And arsenic, you'd have to say it's on the right side, non-metal. Germanium is on the left side, it's a metal. But both of those are used to make computer chips. They're both semiconductors. Enough about the periodic table for now. There's more to know, but we'll get to that in a little bit later. Cool. Let's see, density. Density happens to be a really important property of matter. It's very useful. It's also a good conversion factor. There's a cool story based on truth that Archimedes, a Greek philosopher, actually used the principle of density to prove that a crown is made of solid gold. So I just found this Greek crown here. I'm not sure what it looked like. Maybe it'll look like something like these olive branches made out of gold. Like this cartoon, you know, plan A, hey, let's melt your crown down, king. And then we'll analyze and see if it's pure gold. The emperor didn't really like that idea. No, if you measure the density, and there's a neat little trick, you can do that without destroying or damaging this at all. You can dip it in water and see how much water is displaced. They'll tell you the volume. You can weigh it to get the mass, and the density is defined to be mass divided by volume. You can measure it. And if you get a measurement that's close to the known measurement of the density of gold, 19.3 grams per milliliter, then that's good evidence that the crown is made of pure gold. Neat. This is a formula you should memorize. Sorry, yet some more memorization. But there's a cool little trick. Just repeat after me. I love density. I love density. I love density. No, I don't. So if you cut that heart in half, kind of make up the letter M above here, divided by the letter V down here, maybe. That's the formula for density. Mass M divided by V. Cut that in half. I got the M over V. Nice way to remember the formula for density. Pure water has a density of 1. I don't ask you to memorize that, but I do want you to know that this value, 1 gram per milliliter, is only true for pure water. You dissolve something in it, let's say salt, then you're adding the mass of the salt to the water. You're making it heavier. You're changing the mass. Okay, so now the density of salt water is not going to equal 1.0 grams per milliliter. Let's see what else you need to know. Oh, it's a conversion factor. What does that mean? Well, density of water, let's keep using water as an example, is 1 gram per 1 milliliter. Or if you have 1 milliliter of water and it's pure water, then you know you must have 1.0 grams of that water. If you have 50 milliliters, well then, the density of water is 1 gram per milliliter. So the milliliters, oops, the milliliters will cancel. Scroll this down so I don't hit that again. The milliliters will cancel. And then you'd have 50 times 1, which is 50 grams. Now let's see, I should probably pay attention to significant figures, right? So 50, that's a little ambiguous, but let's say the 0 counts. We have to be told that, right? 0 that follows digits and is before the decimal place, that may or may not count, but I'm going to count it today. 2 sig figs here, and then there's 2 sig figs here, so my answer is going to have 2 sig figs. Cool. Oh, neat little point about density. You dissolve something in it, that changes the density of it. And if the density of an object, liquid, solid, or gas, if the density is less than 1 gram per milliliter, that means it'll float. So if you get a full can, unopened can of Diet Coke, unopened can of regular Coke, throw it in a bucket of water, the Diet Coke will float. The average density, you have to average the density of the metal, the aluminum can, the metal aluminum container, the liquid inside here, and maybe a little gas at the top. take the average density, it's going to be less than 1. And now this whole can is floating. Why is that? Well, it's carbonated. What does that mean? Carbonated means it contains dissolved carbon dioxide gas. And the gas dissolved there in the water is making it less dense. Also makes it fizzy. And so that makes overall it's less dense and it floats. But if you add a whole bunch of sugar, that's going to increase the density. So this very sugar-rich solution that we call Coca-Cola, the density is more than 1 gram per milliliter. So that's sinking. Cool. Oh, and density. Let's take a look at temperature changes. Okay. So we got a little math over here, but first I want to get a fundamental understanding of the concept. So the idea is that if you add or remove heat energy, that's going to change the temperature of an object, whether it's a gas, liquid, or solid. That's pretty straightforward, right? You warm something up in your hands, the object gets warmer. You stick something in the refrigerator, pull the heat energy out, it's going to get colder. That's all we're saying. But now we want to do a little bit more scientifically. Let's get some measurements going here. So how much? I want to measure how much heat energy is going to go in or out of this object. Well, that's going to depend on 3 things. First, how much of this object do I have? Do I have a little cup of water I'm going to put in the microwave? That'll be easy to heat up. Or am I talking about the whole bathtub of water? So I need to know how much material I have. I'm going to measure that in grams. Measure the mass. It's going to tell me how much of the object I need to warm up or cool off. I also have to be told what material I'm heating up. Am I heating up water? Am I heating up a piece of wood? Am I heating up, I don't know, a volume of air? Are we heating the house, right? In the wintertime with our furnace. It's actually going to be a conversion factor, but the amount of heat that's required to change the temperature depends on the object itself, the material it's made of. We're going to call that specific heat. That's something you'll have to look up or be told. And finally, the amount of heat energy that you need to remove or add in to change the temperature, well, it depends on how big a temperature change do you want to do. It depends on where you start and where you end, the change in temperature, right? So if you're just taking lukewarm water and just warming up a little bit, not much heat energy needed. But if you take cold water and you want to heat it up to boiling, that's a big temperature change that needs more heat energy. Okay, so that's how we're going to calculate it. How much heat energy is required? Well, let's find out how much of the object we have, its mass. Tell me what type it is. We'll get the conversion factor that's called specific heat. And then also tell me how much of a temperature change you want. In algebra form, we're going to use the letter Q to represent the heat energy, the letter M to represent the mass. We'll abbreviate specific heat as SH. And the change in temperature, well, we're going to subtract. So what's our final temperature minus our initial temperature? Okay, I will give you this equation on exams. So you don't have to memorize it. You just need to understand it and be able to use it. The Greek letter delta means change. So you have to know that delta T means, oh yeah, take my final temperature, subtract it from my initial. Also pay attention to the units. The specific heat's the weirdest one. We'll explain this in the sample problem. That'll make more sense there. Cool. Okay, so let's take a look at the example here. So this could show up on your first exam. I think I got your attention. How much heat is required to warm a 5-gram spoon from room temperature, which I'm going to define as 20 degrees Celsius, we'll use the metric system, up to body temperature, which is about 37 degrees Celsius. Cool, all right, so how much heat? How much heat? That's Q. All right, so I need to know what Q is. Put that down, start showing my work here. Q, I don't know what that is, I'm trying to find it. Times mass times specific heat times the change in temperature. That's what I want to know. The mass, that's 5 grams. Specific heat, that's the material. Oh, it's a spoon. Wait, what's the spoon made of? Oh, it's made of stainless steel. So I go over here to the table. Again, you have to be told or be informed as to where do you look up specific heat. Stainless steel is not on the list, but iron is. It's right here. So let's scroll over. Give me the mouse, please. There it is. And we see that iron has 2 numbers. Okay, so go to the top of the column, and we got something in joules, and we have something in calories. So it turns out, back here, we're going to use units of calories. So I'll try and stick to that on the exams. I'll just stay with calories. You can measure heat energy in joules, but I'll try not to do that on exams. Okay, calories. So I want this second conversion factor for iron. It is 0.11. That's this number right here. 0.11. And the units are calories divided by grams times, oh God, there were times degrees C. That's what it says. Those are the units. I'll put that whole thing in parentheses because that's just weird. Now I multiply it times the change in temperature. What is the change? Is it 20 minus 37 or is it 37 minus 20? Ha! In this intro level course, I'll take either one. You're going to get the same numerical answer. It'll just have a minus sign in front or a plus sign in front. And it turns out I just want to know what the heat energy is. So if you subtract 20 from 37, full credit. If you subtract 37 from 20, full credit. You're off by a minus sign or plus sign. And this is Chem 6 intro. We want the basics, so I'm going to be lenient. Technically, though, it's a final minus the initial. Not going to have enough room to put the degree C, sorry. It's okay, I hope. Okay, what does this do? Well, I got a gram here. Cancel out the gram here. 37 minus 20 is 17 degrees Celsius. Now the degrees cancel out. These 2 units went away. I'm left with calories. Good, that's what I want. I want the heat energy measured in calories. So now we go get your calculator and take 5 times 0.11 times 17, and you get, well, the calculator can get you something with 19.61 or something. I hope I'm looking at my number here on my scratch work. No, it's around 9.01. How many sig figs are in my answer? When I subtract, I keep the same number of decimal places as the one with the fewest decimal places. Well, those are all whole numbers. So they all have, it's all the same. The decimal points right after whole numbers. So I got 2 sig figs here. I got 2 sig figs here. I only have 1 sig fig here. So I only can keep 1 sig fig in my answer because I'm multiplying. So it's a 9. And the units are calories. Cool. Darn, I'm looking at the time. I don't have enough time. You repeat the calculation for ice. You're going to use a different conversion factor, that's all. And what you're going to see is it take, because the conversion factor is 0.5 versus 0.1, it's greater. It's going to take more heat energy, even though you're changing the spoon, the temperature of the ice and the spoon by the same number of degrees. It just takes more heat energy because it's made of water, solid water. So it requires 0.5, not 0.11. If you had water, that's all the way up to 1 instead of 0.1. And so I'm telling you this because that'll help answer this last question. I was trying to find some relevance, so I'm reaching. But the question is, why should you not cook with a metal spoon? Well, this metal spoon only took 9 calories of heat energy. and it raised it from 20 degrees up to 37. 9 calories is not very much heat energy, and it quickly raised the temperature. So you shouldn't cook with a metal spoon because the metal spoon will quickly heat up and it could burn you. It's also a conductor. So it conducts heat energy really well. Oh, finally. Oh, let's see, I got the candy bar over here. I want to just point out one thing here. You've heard of calories before. And it turns out that I'm talking about a different type of calorie. These calories are a scientific unit for heat energy. So 9 calories to warm up the spoon. But these calories have a capital C. And it turns out that's a food calorie. It turns out that's equal to 1,000 scientific calories, the lowercase c. And this is not on exams. This is just something interesting. So scientifically, we're going to do all these calculations for changing the heat, changing the temperature, and measuring the amount of heat energy in units of calories. I just wanted you to be aware we're off by a factor of 1,000 between scientific calories and food calories. Why? I don't know. World's weird. No, I think there's a good reason. They probably thought about one time putting labels on here with the actual scientific calorie. But if one food calorie is equal to 1,000 calories, then this candy bar would have to be labeled as 130,000 calories. That's what it is in terms of scientific calories. And who's going to eat that, especially if they're trying to watch their weight? 130,000? No way. Okay. Anyways, I'll see you guys in the next video. Take care.